The paper I read, the name is Lattice-Based Cryptography in Miden VM. Actually, it's not introduced how the lattice-based cryptography in Miden VM is about how to introduce lattice-based cryptography to Miden VM. I just take a lattice-based cryptography dilithium as an example to see how we introduce this scheme into Miden VM. Yeah, so the goal is we introduce this to Miden VM. There are a couple challenges, such as for just draw a table. Is Miden. The first is the field they use is different. In dilithium, the field, no, I think it's the ring. It uses the ring to do the multiplication. It calls ring Q, RQ, N. Q equals to, Q is a prime, Q don't have to be a prime number. The value here is 2 to the 23 minus 2, 13 plus 1. And the Miden VM, it uses Goldilocks. So it has this parameter is P 2 to the 6, 4, 2 to the 2 plus 1. Yeah, so the challenge is to, if we put this scheme to Miden VM, then you need to, because the operation here is a ring operation, so we need to simulate the ring operations here. So that's the challenge. The solution is, if you satisfy this condition, it will be fine. The condition is P larger than 2n q squared. Yeah, so this will solve this problem. I will not explain this one because I can't. The second one is today we will explain in more detail is the FFT. In the paper it called NTT, it's the same thing. The FFT, the challenge here is that dilithium is just okay. We just use the normal way to do the FFT operation. But in Miden VM, it has a word. This structure, the word equals to 4 field element. Here. And each element is under this Goldilocks curve. It is 6-bit. So word is equals to 4 times 64 bits. You have this one. The challenge is that when we do the, I will show later, when we do the FFT, word is like this. You have the challenge is that normal FFT, we just do the multiplication A0, A1 to A minus 1. But here, if you use word, then you need to group them together, A2, A3, and like this. So how do the FFT with this kind of structure? So that's a challenge. The solution here is, we have a FFT for this 4-element word. So my talk will focus this part, how we resolve this one and get our final solution. So I will start from a normal FFT. The normal FFT is, we write this polynomial as a coefficients way, such as A0, A1, A2 to A7. So the normal FFT, you do the divide and conquer. So first you divide. The way to divide, a quick way is you use bit reverse. Or you just recursively divide them as each layer as even and odd. So each time you divide them to even and odd, and finally you will get the same result. The final result for this, the coefficients is, I just write down the final result is A0, A4, A2, A6, A1, A5, A3, A7. So after we divide this, we get this, then we do the conquer part. We combine them together to our final goal is we want to evaluate all the evaluations with this subgroup is 1 omega square to the omega to the 7. So here we want to evaluate them, all these 8 values. Then I will show how to do this. The way to do this is there is a formula to calculate. Is we have fx equals to, I just add a layer, then I will show how we use this layer to calculate. Actually, this formula is, if you divide them as a even and odd, so it's this form. Okay, next I will show how to do the evaluations from the coefficients you got with this bit reverse, and finally we'll get all the evaluations and finish the FFT. Now you have a 6, 8, 4. Okay. So we write down the binary representation of this one. It will be 0, 0, 0. And it's this layer. The layer is this one. And the last layer, because it's a constant polynomial. So we evaluate this one on this subgroup, multiplicative subgroup. The group generators only have one. So this one will equals to this. This one will be 1, 0, 0, 1. Will be 0, 1, 0, 1. 1, 0, 1. The next layer is based on another group. We also need to evaluate different values on this subgroup. The subgroup will become I write here 1 minus 1, and it will be we just remove the first digit, then we will get this polynomial. 1. Next will be 1. 1. Then we will apply this formula to get the layer values. So you can see that you only have coefficients, then you can combine them together. So the way is that you can get this value from these two. So x here is 1. And you can get this one with this formula. So you have x is minus 1 here. Then you can continue to do this one, then you will get all of them. Next layer will be similar. And finally, you will get all this. I think there will be another layer is 1 omega square minus 1 minus x squared. And the final layer will be 1 omega square omega. So that's all the evaluations. Yeah, so that's a normal FFT, how it works. Then how apply this four field elements. The first method is you can just do FFT 4 times. It's very simple. You just, because there are 4 elements, then you can just do 4 times separately. The second one is will be better, and it's just optimized for this 4 element word. And I think the idea is quite simple. If you look at these 4 values, you can take it as a 8 element array. Then actually you can just divide it as a 4 element array. It will be something like this word. And for what does the word mean? The word, it means that for the Miden VM, the 1 cycle, you get 1 word. So we just need to optimize this algorithm with this word, because you only have 1 word data for 1 cycle. I remember that there is a arrangement is different with this coefficient. In Miden VM, the coefficients is like this: A0, A5, A1, A4, A1, A5. This one will be A2, A6, A3, A7. So first, in Miden VM, the first cycle, you get this word. Then you just apply this algorithm to calculate these 2 and these 2. So next cycle, you get this word. Then you just do this one and this one. Then all the following algorithm will be the same as the normal FFT.
So does that mean, so if I want to normally evaluate a polynomial with 8 elements, so we need to wait the VM 2 cycles, right? Yeah. So it seems like I need to wait the Miden VM 2 cycle and generate 2 words.
Yeah, I think you need multi cycles. I just take these 8 elements as an example, but actually the polynomial will be much larger than that.
Okay.
Yeah, I think that's the core idea for how to do the FFT or optimize FFT in Miden VM. Yeah, there is no too much change for the FFT because FFT is FFT. You can not change that. You can just the structure is this layer structure. Then you just do some optimization within this structure.